the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed the population dynamics based on these nonlinear equations, and there we have just considered like two system of equations which are nonlinear in nature, and we have just find this like critical points, and we have analyzed also how the stability is occurring at that point based on like Jacobian matrix. And in the present lecture, we will discuss about discrete time prey-predator model in a second phase. So, in this model, we will just go for first discussion of a prey-predator model, how it is just observed in nature in a different sense. Then, if there is some limitations in the resources, how prey-predator model behaves. So, if you will just see that in the last lecture we have studied about this prey-predator model, where each individual species were having geometrical growth rate, that is like xn plus 1 equals to 1 minus a xn, and we found that both these fixed points are unstable in the last example. And when we are just introducing this logistic growth rate function, we have concluded that this function comes into the picture when there are limited resources or competition for food is preserved. The same concept will be applied here for both these species, because they are only like resources for predators here. This means that we can just say that only this predator is present and they can only eat the prey thereover. So, no other sources it is available to them. Then if we will just reformulate this model, which can be written as like xn plus 1 equals to 1 plus a xn minus beta x square n minus b of xn yn. And then the second species, that is the predator species, which can be written as yn plus 1, this equals to 1 minus c yn plus d xn yn. If you will just see our earlier lecture, you can just find that the only modification we have just included it here is minus beta x square n. This means that if there are limited resources of like prey is available, then this predator population, if they will eat the prey, then this prey population it will be declined by the rate of the total population present in that level. And that is why we have just written it as minus beta x square n here. So, in a clear analysis, if you just see here, if we are just writing here, this function comes into the picture when there are limited resources or competition for food is available. This means that if the prey population is limited also, then the predator they can eat like anything. Then after certain time you can just find that this prey population at certain level they will just get declined. So, that is why we have just write it here that this population level it will be declined in a like square form here. So, if we will just go for like fixed point analysis for this model here, then first we are just keeping here that x as lambda 1, since xn plus 1 it can, since a fixed function means we can just put it up here as f of x equals to x. This means that f of lambda 1 is lambda 1 and f of y as y. This means that f of lambda 2 it can be considered as lambda 2 here. And that is why this fixed point modeling can be written as like lambda 1, this equals to 1 plus a lambda 1 minus beta lambda 1 square minus b lambda 1 lambda 2, which is written here. Similarly, if you will just put here that is y as lambda 2, then it can be written as lambda 2, this equals to 1 minus c lambda 2 plus d lambda 1 lambda 2. If we will just solve these two couple of equations, we can just find that first equation it can just provide us here lambda 1 equals to a by beta, then we can just get lambda 2 equals to 0. Similarly, if you will just put here lambda 1 equals to c by d, we can just get this lambda 2 as a by b minus beta c by bd. So, these are this like critical points we can just get for this system of equation here. And for this fixed point like 0 0, if you just find this Jacobian, for the first Jacobian we can just differentiate this one with respect to x here So, if you just differentiate this one with respect to x here, then we can just find 1 plus a minus 2 beta x, then the last term you can just get it as like minus b y n, and for the second term if you just differentiate this one with respect to y here, then you will have like only minus b x n. Since we are just putting here x equals to 0 and y equals to 0, so that is why this complete term is 0 here. Similarly, for the second equation, if you just differentiate this one with respect to x here, then you will have the term like a d of y n here, and if you just differentiate this one with respect to y n here, so it will just give you 1 minus c plus d x n. So, 1 minus c plus d x n, since x n equals to 0, it is just giving you 1 minus c. Clearly, if you will just see, the eigenvalues are nothing but 1 plus a and 1 minus c here, since these are the diagonal entries only. And for the fixed point 0 0, we can just say that it is a stable point if the eigenvalue should be less than 1. So, first eigenvalue if you just consider here 1 plus a in absolute form, if we can just consider it as less than 1 here, this implies that in the manipulation process we can just get a should be lies between minus 2 to 0 here, and this is not possible since a cannot be negative, and the fixed point 0 0 is unstable here. For the fixed point like a by beta 0, if you will just analyze here, then if you will just put here x as a by beta and y as 0, then the reduced Jacobian will take the form of like 1 minus a minus b into a by beta 0 and 1 minus c plus d into a by beta here. And if you just see, this is a upper triangular matrix here. So, in case of upper triangular matrix, already we have known that the diagonal entries are nothing but the eigenvalues here. Hence, the eigenvalues if you just see 1 minus a and 1 minus c plus, we are just representing here dk, where k is nothing but a by beta we have just assumed as the maximum carrying capacity. This means that we have already discussed in the previous lectures that if suppose your initially the population level, if you just consider this is the time level in this direction here. So, sometimes we can just find that if this is the origin here, then the population level, if it is just starting at a lower level, then it can just grow it off for the prey size if you just see without the presence of predator, and if the predator is present there. So, if the predator will just eat the prey, then after certain time you can just find that this predator population will goes down when this prey population will be less. So, then at a level you can just find that when there are both these species are coexisting, then it will just maintain a maximum carrying capacity. So, that is why we have just maintained a maximum carrying capacity value as k here, which takes the ratio of a by beta. And the stability of a fixed point a by beta 0, which will depend on this like eigenvalue here, that is the magnitude of eigenvalue for both these eigenvalues. If you just see here, we have assumed that a is greater than 0, since this is the rate of population growth for this like prey population here, and if a is bounded at 2, then we can just find that if a lies between 0 to 2, then 1 minus a is less than 1 here. Now, if we will just consider the second eigenvalue here, that is 1 minus c plus dk, since we know that c should be lies between 0 and 1, that in the earlier lecture we have discussed, then we can just find that 1 minus c should lies between 0 and 1. So, if you will just define a Grace loss ratio term, that is in the form of mu here, which is defined as k by c by d. So, the eigenvalue can be written as like 1 minus c plus mu c here. So, for the stability we have to consider that the absolute value of 1 minus c plus mu c, it should be less than 1, and if you just put this one as less than 1, then for a further like manipulation we can just get it as minus 1, it should be less than 1 minus c plus mu c, this is less than 1, where we are just obtaining this relationship that is in the form of 0 less than c into 1 minus mu, it should be less than 2 here. So, if we will just go for this stability analysis of prey-predator model for limited resources, now we observe the last inequality that when C lies between 0 to 1, if mu greater than 1, it will not satisfy the stability condition, and hence we will make the fixed point unstable here. And if we will just assume also mu lies between like 0 to 1, it will make fixed point asymptotically stable, if we will just see this point here. Now, the question is that what is the biological meaning of the gain loss ratio mu, whatever we have just defined now. So, mu is nothing but we have just defined as like a maximum carrying capacity to the ratio of like C by D here. So, if you will just see here, if mu is less than 1, that is k is less than C by D, then it will makes the fixed point stable, and k is the carrying capacity, and the ratio C by D signifies ratio of decline rate of predator in absence of a prey to affect the interaction with prey on predator's growth. This means that if like a prey will be reduced, then definitely we can just find that the population growth of predator will increasing. So, heavily if they will just consume this prey population, then the predator will be like increased, but the prey population will be declined in that level. If C is high, then it will make predator to extinct at faster rate in absence of prey. This means that if like no deers are present, then tigers will die out in exponential form, which also implies that interaction effect will be less on predator and vice versa. So, overall C by D is affecting this factor here. So, C by D will show the loss of predator population, and if D is high, suppose if you just consider that the predator has high effect due to this interaction, which will make the prey population to decline at much faster rate, and the same will affect the predator's population at larger stage. So, if heavily this prey will be consumed by the predator, then initially we can just find that this predator population will grow like faster, but after certain time we can just find that if the prey population will be very less, then this predator population will be declined. So, if in both these cases, if you will just see C by D signifies the loss of predator population, this means that we can just conclude the ratio mu, it is just termed as a gain to loss ratio biologically. If gain is greater than loss, then the system should be stable, always it should be there. So, when mu less than 1, then we can just find that gain is always greater than loss, and we will have like a stable condition. But if you will just find that the value mu is greater than 1, then we can just find that the system is unstable there. And for the steady state, if you will just assume this point as like C by D, A by B minus beta C by beta D, the Jacobian can be written as like 1 minus beta C by D minus B C by D, and D into A by B minus beta C by B D 1. Since if you will just directly put these points in the equation, like whatever we have just determined by differentiating this first equation with respect to first x, then y, then the second equation with respect to x, and the second equation with respect to y, here these equations. Then directly if you will just put these values, we can just find this Jacobian as this form here, and the characteristic equation definitely if you just put here minus lambda and minus lambda, if you just find the determinant equals to 0, then we can just obtain this equation here. There is lambda square minus lambda into 2 minus beta C by D plus 1 minus beta C by D plus SC into 1 minus 1 by mu equals to 0. And the eigenvalues, if you just find it out, the eigenvalues can be written as a 0.5 into 2 minus beta C by D plus or minus 0.5 square root of beta C by D whole square minus 4 AC into 1 minus 1 by mu here. And if we will just assume here that mu should be less than 1, then 1 minus 1 by mu, it should also be less than 0, implies one of the eigenvalues that 1 lambda greater than 0.5 into 2 minus beta c by d plus 0.5 square root of beta c by d whole square, or lambda greater than 1 here. So, fixed point will not be stable for mu less than 1 and will be asymptotically stable for mu greater than 1 here. And in this model we have discussed like a prey predator model, where we have just considered like different resources if it is available for this prey and predator. Like we have just assumed that the fixed limited resources of prey is present, then how predator is just performing, or how this prey population it is just behaving there in the first sense. And second level we have just discussed that if there is a limited resources is available, how this prey predator model behaving, or how this stability condition is achieved if we are just assuming this Jacobian matrix there. And till now we have discussed like first we have discussed mathematical models based on like deterministic and stochastic form. Then in the discrete time system, which involves like difference equations, we have discussed this linear models and nonlinear models. And this nonlinear models that includes like nonlinear cell division model, survival function, competition, contest competition, scramble competition, all this we have just considered. With this we have included like a Beaverton-Holt model and Hassel model. And for this continuous time system we have involved here like ordinary differential equations and partial differential equations. And for the nonlinear prey predator model we have included like without limited resources, with limited resources. And for the logistic difference equations we have discussed like its applications, formulations, then the graphical analysis, then how we can achieve the stable solutions, then periodic solutions, and also we have discussed like a chaos, since 3 different cases we have just considered like the values of R as we have taken, that is 2.2, 3.3 and 3.33. Finally, we have just considered 3.9 to get the chaos. Then we have just introduced the bifurcation, like a different class of bifurcation, how it is just included in the physical problems. So, first one is the saddle node bifurcation, then transcritical bifurcation and pitchfork bifurcation. Whatever these other bifurcations that are just discussed or people are studying based on these like 4 bifurcation methods. So, last one is the periodic doubling flip bifurcation we have discussed. So, finally, we have just discussed about the stability analysis based on fixed point, then the linearization using the Taylor's method, and this stability analysis is studied by this Jacobian matrix form. Thank you for listening this lecture.